Thank you very much. Can you hear me? Is it this thing on? Yeah, good. So the story I'm about to tell you about happened long, long ago, far, far away. And to be more precise, it was like roughly 120 years ago, somewhere in Europe. And what happened there is, I think, the single greatest revolution that took place in science ever, that shook the world of physics. And until this day, people are still kind of not woken up yet from the shock that they discovered in the beginning of the 20th century. And what I mean by this whole thing is basically discovery of quantum theory. And that discovery was so strange, so difficult to embrace that, most of the people still up to date discuss what it actually means, that word is quantum. And what I want to do today is basically show you what it means that the word is quantum. And just to give you some historical background, the whole discovery was not made by a single person. It was made by a bunch of people. And just to give you the scale of this whole discovery, let me tell you that for the discovery of quantum theory, there was more than 9 Nobel Prize winners just for the discovery of the whole theory. That included Planck, Einstein, Bohr, de Broglie, Heisenberg, Schrödinger, Born, Pauli, and Dirac, and many others. And those were the times where, unlike today, when you get a Nobel Prize, you become a hero and a celebrity. In those days, these people elevated the prestige of the award by their names, and they became heroes of physics forever, I guess. Every student knows their names. What is very interesting about the quantum theory is that half of those people, roughly, did not believe it. Like, they discovered a theory, they contributed to the discovery, and then they stopped believing. Planck did not believe the theory. Einstein, until his death, doubted quantum theory. De Broglie did not believe the theory. Schrödinger hated it. He just hated the theory he created him own. And there was this debate going on between these guys. History of that is very, very interesting. I'm going to give you some glimpses of that. But that shows you kind of what kind of revolution we are dealing with. And it's worth remembering that Einstein himself was the author of special and general relativity, which was another breakthrough theory that shook the world of physics. So he was not just a mere mortal. And he himself, being able to embrace new ideas, he was unable to kind of agree to what quantum theory seemed to tell us about the reality. So let me give you some quotes just to illustrate the situation after people were trying to understand the world of quanta. This is Schrödinger. If all this damned quantum jumping were real here to stay, I should be sorry I ever got involved with quantum theory. Wolfgang Pauli, young genius. Physics is very muddled again at the moment. It's much too hard for me to anyway, and I wish I were a movies comedian or something like that, and I had never heard anything about physics. Hendrik Kramers. The quantum theory is much like some victories. For a month or two, you're laughing, and then you cry for long years. I agree. Lorentz, one of the creators of special relativity. I have lost the conviction that my research was leading to an objective truth, and I do not know what I have lived for. My only regret is that I did not die 5 years back when everything still seemed clear to me. Now, the opposed statement comes from Woody Allen. My relationship to death remains the same. I'm strongly against it. So you can see people were really moved by the whole thing. And the most interesting thing about this quantum theory is that it's quite easy. It's not because it's so difficult to understand. It's very easy to understand. And the purpose of this talk is to show you what the quantum theory is and why is it so strange. It's not, the problems are not because it's difficult to understand, but it's more because it's difficult to kind of be in peace with what you learn. So it's just difficult to accept. And I'll let you be the judge. You can make your own choices, whether you like it or not, whether you believe it or not. Let me just tell you that up to date, there was no a single experiment that has been performed that would disprove quantum theory. Every single experiment we have ever done from those days up to now, which took 100 years, and believe me, people tried really hard, is in agreement with predictions of quantum theory. So I believe it's really so simple that you can actually understand all these paradoxes, all these difficult things, or strange things, by thinking about a piece of glass. That's all you need to know. Just imagine a piece of glass and the light that goes through a glass. I think we can make very simple thought experiments to kind of understand what these problems are about. So imagine a piece of glass. Piece of glass is basically some material that has a property that it can transmit the light through. But when you have a piece of glass, you also know that it always reflects a little bit. If you look at a window, you will see a reflection. So every glass reflects more or less some part of the light that falls. And we can imagine that we have a piece of glass that reflects exactly 50% of light that falls on it. So imagine you have some light falling on the piece of glass, and it reflects half of it, and it transmits half of it, which we can verify by placing two detectors that measure intensity of light. Now, at the beginning of 20th century, people have realized that light actually consists of particles. Like all the matter that we know, that consists of atoms, elementary particles like electrons, protons, etc. Also, light consists of particles. Those particles are called photons, and they are very simple objects. When you have a lot of light, that simply means you have a lot of photons entering your eye. So let us now imagine what happens if we think about the beam of light as a bunch of photons that fall onto the beam splitter. Well, in this experiment, it means that half of those photons gets reflected, half of those photons get transmitted through the glass. And now, let me ask you the first simple question. All these photons are the same. If the light is red, has a given polarization, that means every photon has the same color, exactly the same polarization. They don't differ at all. They are very, very simple objects. So you know that some of them get reflected, some of them get transmitted. What causes a given photon to reflect or to go through? They are just identical. So this experiment is like repeating many times, illuminating a beam splitter, as we call this piece of glass, illuminating with a single particle of light, then repeating, many times repeating, and sometimes the photon gets reflected, sometimes it gets transmitted. Why? What causes that? It's like repeating every time the exact same experiment. Why do we sometimes get result like this, and sometimes we get a result like this? What do you think? Probability, well, okay. Well, probability theory, I have a coin in my pocket, so I could toss a coin, and there is a 50% chance that I'm gonna have heads, 50% chance I'm gonna have tails. But every time when I'm tossing the coin, I'm doing it in a slightly different way, right? Maybe my fingers like shake a little bit. Maybe the air in the room is moving a little bit, so the coin collides with the air in a slightly different state. Then maybe it's falling on the table and could fall in a slightly different place. The surface is not exactly flat. So I'm not controlling all these parameters. That's why I'm not repeating the experiment exactly the same way. And that causes semi kind of chaotic behavior, semi-probabilistic behavior. But here, I have very simple objects. It's like repeating the exact same experiment without any change at all. So Einstein could not believe this probabilistic situation. He said God does not like dice, as somebody said already. And he thought, well, these photons have to differ. They cannot be the same. They must differ somehow. We don't know exactly the structure of a photon. Maybe there's some more complicated theory we haven't discovered yet. They must be different from each other, and that causes the different behavior. So let's imagine that those photons do differ by some parameter. Let's say that some of them have hair and some of them do not. All right? So let's assume that those that have hair go through, and the bald ones just get reflected. Now, it means that we have just filtered out all the hairy photons, and now if we repeat the experiment by placing another beam splitter here, we should expect that all the photons go through, because now they are identical. We repeat the experiment. What turns out, again, they split 50-50. And people have performed many, many experiments to verify that, to try to at least shake this probability distribution a little bit. It was always exactly 50-50. So it was virtually impossible to capture those hidden hair on the photon by this type of filtering. So it seems like all the photons are the same. What are the other options? Well, another option would be that if the photons are the same, maybe there is something going on in this piece of glass. Maybe this is not a static device, but maybe there is something going on inside the glass that causes the different behavior. For instance, there are atoms inside, they are shaking a little bit. Sometimes the photon could fall here, sometimes slightly in a different place, or the atom could have moved inside the glass, who knows. So there could be some hidden mechanism inside that causes some photons decide to reflect, some photons to go through. Before I comment on this, because I want to show that this is not the case, and we can show that this cannot be like this, I'll tell you what quantum mechanics says what the answer to this question is. Quantum mechanics says there is no reason for a photon to reflect or go through. The act of reflecting or going through for a single particle is completely random, as we say, indeterministic. There is no law of physics that will be able to explain the behavior of a single particle. Which is kind of shocking, because physics was a tool to predict the future, as we think about it. Like classical physics was a tool to predict the future. If I throw a stone, I can predict where exactly it's gonna fall. I can calculate the distance. If I know the exact initial conditions, I can compute, predict, use laws of physics to say what's gonna happen next. Here, apparently there is no law of physics that will tell you what's happening to a single photon. And quantum theory says, on the fundamental level, there are no laws of physics with regard to a single measurement on a single particle. There are only probabilistic laws. So we can calculate probability of a certain event to happen, but we cannot have certainty. Einstein couldn't take it. He said, God does not play dice. Okay, so, but before we kind of convince ourselves about this, we still have to investigate the possibility that there is something going on inside the glass, because perhaps there is some deterministic mechanism in the glass that decides about the behavior of a single photon. So in order to rule out such a possibility, let us consider a slightly more complicated version of our experiment. So let's again have a piece of glass and light shining onto it, and let's add a little bit more elements. So the light is partially reflected, partially transmitted. Let's add two ideal mirrors, here and here, that just reflect the light. And let's add one more piece of glass here. That's, again, has the same properties as this one, which is repeating, transmitting half of it and reflecting half of it. And two ideal detectors here and here. What happens next? Then the light gets reflected here from the mirrors, and the question to you is, what's going to happen next? Where the light is going to end up in? Which detector? What do you think? If you were to guess. There is no quantum theory here. It's just a classical light. So it may be a slightly bit more intuitive for you. Half and half, yeah. Any other suggestions? Yeah. The right answer is it depends on the details I haven't specified. And those details are the distance that the photons, that the light can go through. That's one way. But even if I assume that distances, the distances are the same in both ways, if the distance here is exactly the same as the distance here, there is still one more thing I have to specify, namely the thickness of the glass. Because imagine the light goes into this detector. that means it could go either this way, reflect here, reflect here, reflect here, and go here, or go through the glass, reflect, and go through the glass. And light going through the glass gets delayed because it moves slower in the glass. And if you think about the light as some sort of electromagnetic wave, which is the way to describe light using classical theory, then a wave, you have a wave here, you have a wave here, the one going down gets delayed, and then they overlap on this piece of glass again. Now, if you choose correctly the width of this glass here and here, the light going in the lower path could be delayed exactly in such a way that the ups or heels of this wave here will exactly coincide with the bottoms of this wave here. And if they do, they're just going to cancel out. If you have two waves where the heel meets the bottom, they just cancel out, there's nothing out. And if you choose the width of the glass to be exactly that, these lights cancel out, it turns out that the light going to this detector exactly coincides such the heels meet the heels and the bottoms meet the bottoms, and all light goes in here. So it is possible to choose those widths of the glass such that all light goes in here. So this is classical physics, nothing to do with quantum physics. This has been known for 200 years at least. So let us assume that we have such a setting with two pieces of glass, two mirrors, that are chosen such that all the light goes into this detector. And now let us ask a difficult question. What happens if you have a single photon that illuminates the glass? What's going to happen? Same thing. But a photon is like elementary piece of light. It's one of its most important features is that it cannot be split. Like an electron cannot be split into half, also photon cannot be split in half. It's just elementary piece of light. It has this property that's just fundamentally indivisible. So it can either go here or here. And if it does, then, well, suppose it goes up, then it has to decide whether to go up or down, or to the left or to the right or to the higher detector. It has to make a decision. Well, it seems to be like 50-50. But you say it goes to this one. Why is that?
It senses the whole system.
How is that?
You ask,
Okay, well, I'll tell you what the experiment is, okay? You be the judge. So if you do experiment, what happens is this. You wait a bit, photon goes out here. You repeat the experiment with a new photon. You wait a bit, ends up here. You repeat the experiment once more, wait, ends up here, always. You do it many, many times, it always ends up in this detector. What does it mean? It seems to be some sort of, again, this thing that we had to do with the waves where they overlapped, which led to canceling out light going here. We call this phenomenon interference. The two light waves interfere, they overlap each other, that is called interference. And the interference can be either destructive, that cancels out, or constructive, it kind of enhances itself. The photon, single photon, seems to interfere. But interfere with what? There's just single photon. Well, it seems that somehow it splits into halves. One half goes up, one half goes down, then they overlap, interfere, and you get the interference effect. It all ends up here. But this picture seems to contradict what I just told you before, that the photon is something you cannot divide into halves. So what does it mean? Is it divided into halves or not? In this experiment, it acts like it was divided, split it into two halves. But let's check it up. Let's place two detectors here to check out where is this photon. And when we place two detectors, what happens? It's 50-50. So, okay, this is what we have to deal with. We have to somehow understand what's going on here. If we check out where the photon is, it's always in one place. We will never find the photon in two places at the same time. It's always either here or here. You will never ever hear 2 clicks of the detector. Just one. And it's random. But if you take away the detectors, photon acts as if it was in 2 places at the same time. Exactly like it was in 2 places at the same time. Interferes with itself, overlaps again, and then ends up in the lower detector. So it seems that photon knows that it's being observed or not. If it's being observed, it chooses to act differently. If it's not being observed, it acts differently. And let me now draw some conclusions. I didn't say what is the size of this path here or here. The size of this whole device could be huge. We could imagine that actually it takes the size of a whole solar system. Those mirrors could be really, really far away from each other. And those 2 detectors here could be placed at the very last moments. For instance, we could have a photon illuminate this beam splitter. Then we could wait a little bit, having the detectors just ready to be placed in the path or not. And we could decide at the very last moment whether we want to check where the photon is or not. If we don't check, photon goes on and interferes with itself. If we check where the photon is, it decides to be detected either here or here. But the very fact that we can make our choice at the very last moment means that the photon doesn't make a decision about the reflection or transmission here. It waits. It waits till the very last moment, and only at the very last moment here, it decides to be either in this detector or this detector. Which means that there is no decision making here in the piece of glass. There is no mechanism that determines the behavior of a photon in this particular place in space. The decision for the outcome of this measurement takes place at the moment of the detection. Which means that the photon has to communicate with itself, potentially on huge scales of a whole solar system, or even larger than that, and kind of talk to each other. Like talking to each other like this. Okay, I want to be detected here, please don't show up here. And it never fails. It always works like this. So a friend of mine commented on this that, well, yeah, indeed, you cannot explain the experiment by just saying that there is some mechanism inside the glass, but also you can observe that the photon acts like a wife. Like it acts differently when nobody's watching. It's exactly like that. So, as you can see, quantum theory is very, very, very weird. Like on one hand, it's not deterministic. You cannot predict what's going to happen in a single experiment, which is already huge change with regard to what has been known in physics for hundreds of years. But also objects, such as single particles, do not have well-defined position. A photon can be here and here at the same time. And this whole weird law of quantum law of governing photons also applies to all other types of particles. Everything that we are built with, electrons, protons, all the particles, are governed by exactly the same laws. And each particle that builds our organisms is never at one place at once. It's in a way in many places at the same time. Like the photon that is in 2 places at the same time, or even more. If you have introduced more beam splitters, the photon could be in many places at the same time. This is exactly what happens to matter on the microscopical level. So it doesn't really make sense to ask a question where the photon is, because there is no unique answer until you make a measurement. Are there any questions about this so far? Yeah. Yeah, sure.
So what you just said, you're saying that this is also the case for really, really big particles as well?
Well,
Maybe in more than one place.
so experiments like this interference experiments have been made with huge, like quantum systems. Like I think the largest particles that have been measured to act like this were consisting of 60 atoms or more, right? And they still interfered. when you make an experiment with Bose-Einstein condensate, which is a collection of millions of atoms, which you can actually see with your own eye, you can also see those interference effects with millions of atoms. So it seems that quantum theory not only applies to the microscopical level, but there is no visible limit where it stops like being the correct theory. It seems to also agree with the reality on the macroscopical level or semi-macroscopical level, when we can start to see those objects that being quantum with our own eyes. So it seems that nature is just much more weird than we expected. Okay, so Einstein kept saying God doesn't play dice. At some point, Bohr got irritated and told Einstein, stop telling God what to do. I kind of like this conversation. I got a tattoo that refers to this. Well, if not God, somebody else must play dice. So I got a tattoo saying devil plays dice. So this is all very interesting, but I don't want to make an impression that the last word has been said in this whole discussion. And let me just give you some more quotes from people that are much smarter than me, and let's draw some conclusions. Let's first quote Planck. When I began my physical studies in 1888 and sought advice from my venerable teacher, Philip von Joly, he portrayed to me physics as a highly developed, almost fully matured science. Possibly in one or another nook, there would be perhaps a dust particle or a small bubble to be examined and classified, but the system as a whole stood there very secured, and theoretical physics approached visibly the degree of perfection which, for example, geometry has had already for centuries. This was how many years? Like 12 years before he contributed to huge, like the biggest revolution in science that we ever witnessed. Albert Michelson, the guy who made a measurement of the speed of light that seemed to indicate that light always moves with the same speed, whether it moves, whether the source moves or not, or the observer moves or not, that eventually led to the discovery of special relativity. This experiment he made in 1900. So a year earlier, he said himself, the more important fundamental laws and facts of physical science have been discovered. And these are now so firmly established that the possibility of their ever being supplanted in consequence of new discoveries is exceedingly remote. A year later, he discovered experimentally that light always moves with the same speed, which led to the discovery of special relativity. And a year later, Planck discovered that light consists of photons, which led to the discovery of quantum theory. This is, I cannot think of more striking example of short-sightedness of somebody having an opinion. Some more. Max Born. Physics as we know it will be over in 6 months. 1928. Well, to me, physics is like we are just scratching the surface, but what do I know? Stephen Hawking. The goal of theoretical physics might be achieved in the not-so-distant future, say, by the end of the century, 1980. I don't even know how to comment on this. Apparently, people are overconfident of their knowledge of reality. I just give you all these quotes just to summarize this discussion by showing that, yes, we know a lot. We seem to understand that reality is much weirder than we thought, but we shouldn't kind of say the last word. Like, who knows what's going to happen next? Okay, at this stage, you may wonder what all that has to do with David Lynch, because I promised you that there will be some David Lynch in here. I'd like to dim the light. So let me now switch gears and tell you about something else. So when I was a PhD student, I was looking for a new hobby. I had like too much free time, apparently, and I decided to kind of develop a new hobby. I bought a camera and started taking photos. So I kind of thought the most interesting subject to photograph would be people. I started taking portraits, and since I didn't have any models in my proximity, I started to just talk to people on the streets. I would talk to strangers, strike up a conversation with strangers, and taking portraits of these guys. And for instance, this is how I took this portrait. I just met this guy on the street. I took a photo. And that's how I kind of got new models. This is how I met this guy also. I met him on the street. I asked him if I could take a photo. I took this one. And I kind of carried on once in a while, hunting for interesting faces. This guy I met on the street, I got acquainted. He invited me to his place, and I took a photo in his apartment. At some point, I started to take photos of more kind of recognizable people. For instance, this is a well-known Polish actor. This guy here is one of the most hated people in Poland. He is a former politician. He used to be the spokesman of the last communist government in Poland. So I think he is the most hated person in Poland. He wouldn't be able to walk the street without being killed like in 5 minutes. So I also have taken portraits of younger people of different sorts. I kind of always looked for something that is not very typical. I was looking for more unusual models. And I kind of carried on with kind of unusual type of photography. Eventually, I ended up doing some commercial projects. For instance, this is a commercial project for Energizer, the brand that produces batteries. And this is a commercial for batteries. They asked me to photograph people that died young, and the question was how they would look today. And the theme of the campaign was, unfortunately, not every life lasts as long as our batteries. So that's how I did this one. I also continued with Bruce Lee. I also had another idea for another model to be featured in this campaign. You may recognize this guy. Here, the agency had to change the theme of the campaign. Fortunately, not every life lasts as long as our batteries. I also did some other commercial projects, like this is a campaign for Converse, producers of sneakers. I did some editorial work. Here I have a colleague that her profession is investigating insides of the brain, so I did that in a slightly different manner. This was editorial commission, and they never asked me again to collaborate with them. But I also took some more moderate portraits. This is one of the first models I've shown you. I got friends with him, and this is his portrait of his daughter. I love his fingers, like they are so kind of unusual. And I also photographed some like major celebrities. I had a chance to approach people like David Lynch himself. And since he is one of my favorite movie director, he directed my favorite movie, Lost Highway. I preferred just to talk to him rather than take a photo, so I just did it quick, and I had a nice chat with him. And what does it all have to do with physics? So at some point, I decided I'm going to switch to filming short films rather than taking photos. And I was looking for a good topic for a film. And I decided, I had this idea, I'm going to do some short, like 1-minute films about physics, but in a very unusual way. So I thought there's plenty of popular science films that you can watch in the internet. I thought I'm going to do something else, something that can interest you, intrigue you, but not necessarily be one-to-one corresponding to physics, but will eventually lead you to thinking or reading about physics on your own. And this way, I created a bunch of shorts about different aspects of physics, and I would like to show you 2 of them. The first one is about special relativity and general relativity, and it deals with the idea that time, unlike we expect, is something that is not absolute, that it can change its speed. Like time can go slower or faster depending on where we are. For instance, in the gravitational field, time goes slower near the Earth, and it's ticking faster up higher. And this is a known fact that is actually being used in GPS devices. And the second film is about this quantum behavior of particles, of electrons in this case, that can be at several places at the same time. And the excuse for the second film about electrons was actually one of my favorite scenes from one of my favorite movies by David Lynch that kind of fit very well to the idea of description of the electrons. And I decided I'm just gonna recreate the whole scene by myself and yeah, put it in the context of physics. To my surprise, these films got really popular on YouTube. Like within a couple of weeks, it got watched by a couple of million people. So I think that was beyond any thinkable reach of any popular science talk I could give. So I thought it was a good opportunity to popularize physics this way. So let me show you those two short films, and let me continue after the break. That was it. Thank you. So let me continue with the physics now. Proper physics. So I haven't told you the weirdest thing yet about quantum theory. What I told you so far is what we know for 100 years or more, that on fundamental level, nature is not deterministic, it's not predictable, and it's not just the same way of unpredictableness that we have with a coin, it's something more fundamental. There's just no law of physics that would determine the behavior of a single particle, and also these particles can be at many places at the same time. Yeah, let's deal with it. There is no other way of describing it that we know. This is just the best description that we have. Okay, but this is not all. If you combine all these quantum effects with another crazy theory that has been discovered in the early 20th century, relativity, both special and general, it gets even weirder than that. It gets much, much weirder. So let me try to illustrate this. Imagine we have a single photon of a given color. Say, let's imagine a green photon somewhere in space. By that we mean that we have an observer that actually makes a measurement and detects the photon, and the photon turns out to be green. So we have to specify what device we are using to that detection, and it has certain properties. We detect a single green photon. But from special relativity, we learn many interesting things, such that time can go slower here if you are moving, or the color of light can change if you are moving. That's called the Doppler effect. When you observe the same photon from a moving frame of reference, the color of light is actually changing. So that's why the stars that are going far away from us seem to be slightly more red, because they are just going fast and they just go far away, and they move away from us, and that causes the light to change its color apparently to us. And therefore, if a new observer is making the measurement that is moving with respect to the first one, the color of the photon is different. One observer could say that the photon is green. Another observer at the same time will say that the photon is red. But the very fact that the photon is there is out of question. The photon can change its properties, but it's still there. Now, this situation changes completely if you consider observers that are not only moving, but also accelerating. Imagine you have an observer that is sitting in a rocket that accelerates really fast. It turns out that for such observer, not only the color of the photon is different, but also the number of photons is different. So one observer can say he possesses and observes a single photon, and this guy in the rocket will say, no, there are many photons. The most extreme case of this situation is called the Unruh effect that has been discovered in the 70s by Bill Unruh. The most striking example of this is that when you consider an empty space that we call vacuum state in physics. So if you consider a situation where the space is as empty as possible, according to laws of physics, which is described by this vacuum state, it turns out that if this observer sees the vacuum around, the accelerating observer will see many particles around. Not just empty space, many particles. So it seems that not only properties of particles are observer dependent, but their very existence is observer dependent. And we are all made of particles. We feel that they are real, like they are there objectively, right? We feel it, we kind of experience it. But this cannot be more far from the truth than actually what happens in nature. What happens in nature is that this is nothing objective. Those particles, their existence can be observer dependent. And then they can appear or disappear depending on who is making measurements, who is making the observations. Which is kind of hard to believe, but that's the way nature is. You just have to deal with it. And my research is dealing with these things. So my research is devoted over the past couple of years, is devoted to studying the consequences of merging the most interesting quantum effects with the most interesting relativistic effects. So, for instance, I told you that accelerated observer can see particles in the vacuum, in the empty space. But accelerations have very similar properties to gravity. For instance, if you are accelerating in the elevator, it feels like you are becoming slightly more heavy at the moment of acceleration, which kind of suggests that gravity itself is similar to acceleration, which actually was the very foundational postulate of Einstein's to develop general relativity. That seems to be the very fundamental law of physics, that the effects of accelerations are very similar to the effects of, of gravity. Therefore, studying effects of acceleration on quantum systems is similar to studying the effect of gravity on quantum systems. And that's actually quite interesting because if you think about it, that allows you to tell what's going to happen to quantum effects if you make measurements near strongly gravitating systems, such as black holes, for example, which are the most extreme examples of astronomical bodies in the known universe. And what I'm doing in my research is kind of studying what's going to happen to quantum experiments if you perform them in the proximity of a black hole. That would be one example. And quite recently, we wrote this paper with our colleagues studying the consequences of the Unruh effect that were kind of surprising. And we applied those, all these quantum and relativistic phenomena to the very simple, to answer a very simple question. Whether an ideal clock, a device to measure time, can really be built or not. And we gave the negative answer. It seemed to us that we found a reason to believe that an ideal clock, a device that could measure time, will never be constructed. And this, to our surprise, caused media across the globe to be very excited about this idea. In a few days, we got covered by like all possible magazines everywhere. We had to give interviews in all different countries, including languages that we have never heard of. And that was really crazy for a couple of days. All the fora, physics fora, were like flooded with discussions about this. There's this forum, one of the most popular forums fora about physics called phys.org, was discussing this, and the number of kind of the number of comments about this work was topping everything else for a couple of weeks. Eventually, we got detronized by discovery of the gravitational waves, but everything else was basically not stood a chance compared to this. Which is kind of funny because obviously the whole work is quite technical, and there was no way that public audience could understand the very details, but kind of that title was interesting, and we wrote kind of very good PR note that got spread like a virus. So let me tell you a bit about the result itself that we have found. So I told you that special relativity predicts that time can be slowed down in certain situations. For instance, if you are moving very fast a clock, then the clock itself is going to slow down. Right now I'm moving respect to you. So from your perspective, I should be aging slightly slower because I'm moving. And that involves my clock ticking slightly slower, my hair growing slightly slower, my heartbeat being slightly slower, and all physical processes being slowed down. And this is a real fact that has been measured many times. It's a known fact for at least, well, more than 100 years. The same thing happens in gravitational field. If I place two clocks at different heights, the one that is closer to the surface of Earth, that experiences more gravity because it's closer to the Earth, is going to tick slightly slower than the one that's higher. This is also known. This fact is applied in GPS devices. Without it, probably our positioning system wouldn't work so well without taking that into account. So if you imagine a clock that is measuring time, it could be either a pendulum clock or electronic clock or I don't know, atomic clock. There are different types of clocks. But what you expect from an ideal clock is that it will measure time regardless of its acceleration. For instance, if you have a clock that is moving with constant velocity, it should measure the time being slowed down, and it should not be affected by it being accelerated at the same time. What should only matter is the instantaneous velocity, not the acceleration of the clock. But in reality, if you take a clock and you accelerate it, think what happens to a pendulum clock if you accelerate it. It's not going to give you the right reading. It's going to break. If you accelerate too much, any clock is going to break. If you accelerate atomic clock, which is basically a bunch of lasers and atoms trapped somewhere in the optical table in the lab, if you accelerate the whole lab, well, the lasers are going to fall from the table. The whole thing is going to break. So how do we build a clock that is insensitive to accelerations and can only measure time on its own, so to say? How to build an ideal clock? Well, the best candidate for that is a single particle. A very simple object, as simple as it can be, a single particle. How can it measure time? Well, many particles known in physics have a property that they decay into other particles. They don't live forever. They have a certain lifetime, and then they decay into other particles. And that very act of decay doesn't happen at a very well-defined moment because it's a quantum effect. We cannot exactly predict when it's going to happen, but we know the statistics. We know roughly when it's going to happen. We know the average time of decay. And if we have a bunch of those particles, if we have many of them, we can just wait until some of them have decayed, count how many particles are left that has not decayed, and that's going to indicate, in a way, how much time has passed. So a decaying particle is kind of the most fundamental clock we can think of, but at the same time, it's the most robust object we can think of because, I mean, it's very difficult to destroy a single particle. It's as simple object as possible. So we were asking the question whether at least a decaying particle would be a good clock. And it turned out not. That even the single particle like that will be affected by acceleration. in the crucial way if the acceleration is strong enough. And why is that? And it's actually very easy to understand why is that. If you remember the Unruh effect, which says that if you accelerate, even if you're in empty space, you start being surrounded by many particles. So if you accelerate a single decaying particle, from its perspective, it's not in the vacuum state anymore. If you accelerate strong enough, it starts to observe other particles around it. And if it observes other particles around it, those other particles start to affect the decaying particle and its decay time, and eventually they affect the decay rate, and eventually they affect the rate of the clock. So even the simple object as a single particle has to be affected by acceleration, and therefore we don't really have ideal clocks. Ideal clocks are only approximations that can measure time in certain regimes where acceleration is not too strong, or when gravitational field is not too strong. But if the gravitational field or acceleration experienced by the clock is strong enough, the concept of measuring time breaks down inevitably, and there is no operational way of measuring time. So that raises a question whether time makes any sense if it cannot be measured at certain extreme situations. And we honestly don't know the answer to this question, but it certainly raises a bunch of interesting, intriguing other questions. I would like to finish with a quote, because I told you about many different and weird consequences of quantum and relativity theories, and many people couldn't handle that, like including Einstein, one of the greatest geniuses that ever lived, who, until his death, kept repeating that God does not play dice. And the best reply to that, I think, comes from Richard Feynman, one of my favorite physicists. That's what he said. This is the way the nature works. You don't like it? Go somewhere else. Thank you very much.
So we got some time for some questions for Andrzej. So in your discussion of the clock, does that be solved like sort of a longitude problem, maybe in the universe? You know what time it is?
So, sorry, I didn't understand the question.
So one of the solutions to this longitude problem was making chronographers, right, to be able to figure out how far east to west you were.
Yeah.
So could you use something like to figure out how far east to west you were to galaxy or something like this? Get some very high precision.
Well, but like obviously, inability to measure time translates to inability to measure space as well. So, in a way, we are also questioning the ability to measure distances at some extreme situations. So, I don't know if that answers your question.
I don't know if I have a question.
When you said that when a particle is getting accelerated, it starts to notice the particles around it, even if it's in a vacuum.
Yeah.
What did you mean by that? If there are no particles around it, how can you...
Okay, so basically this is the Unruh effect, which is kind of not very simple but quite complicated and technical effect coming from quantum field theory. But the effect is that if you take the vacuum state of a quantum field and transform it to a uniformly accelerated frame of reference, it's not a vacuum state anymore. Which means, and what you see when you accelerate, you see particles around them, around yourself, and they have all properties of just normal regular particles. And that also affects any accelerating object such as single decaying particle, because from its own perspective, when it's accelerating, it's surrounded by other particles, even if the whole situation takes place in something that you'd call vacuum. So, I mean, it's just, it's quite technical consequence of quantum field theory, but it affects all systems, observers or particles. Whatever accelerates feels many particles around. Yes?
I'm wondering about the actual definition of time, because every particle sees a different time.
Yes.
We can have atomic clocks that you can measure essentially millimeters of change in gravitational field.
Yes.
If every particle in the universe is running on a different time, why are we all still together?
That's a good question. I don't know. I mean, perhaps the answer is that we don't experience those extreme situations. The fact that different particles accelerate slightly different way, or they are in different positions, that causes their ticking to be slightly different, but those differences are really tiny. So we don't really notice them. Like we don't notice relativistic or quantum effects in our everyday life, because we are far from those extreme conditions. But certainly, if you crank up the parameters, if you increase gravity, and even you don't have to reach the quantum gravity scales, it's just very strong classical gravitational fields, you already start to encounter situations where there is no operational way of measuring proper time, as we define it in or general relativity. So the whole theory of general relativity or special relativity is based on the concept of an ideal clock that is basic to constructing a frame of reference. But it turns out that if you take into account the quantum effects, there is no way of actually doing that. So the whole construction fails. So my kind of understanding of this is that that sets limit for applicability of theories such as general relativity in the operational meaning, even before, way before we reach quantum gravity scales. So you can think about ideal time, but you cannot really measure it in any way. Yes.
So would you describe the problem of the ideal clock that based on like the matter that we have, it seems like it's impossible to build something that's not affected by anything else? Like anything we have, it'll be affected, so we can't
Yes.
measure it?
Yes.
Or would you describe it as like a conceptual error that we're trying to measure this ideal time, but there is no ideal time that we're trying to measure, so we just don't understand?
I would say the following: if you take any clock you want, a pendulum clock or atomic clock or any type of a clock you can think of, and move it with constant velocity, they are all affected in exactly the same way. Say I'm moving right now, this clock is delayed the same factor that my heartbeat. These both clocks, my heart is also some sort of a clock, they are all affected in exactly the same way. When you accelerate, every single physical system that could be used as a clock will act differently. And there is no universal clock that can be used as a kind of like golden measure of time when you accelerate, when you take into account all these non-inertial effects. So this becomes a philosophical question, whether you can think about time as something that exists and ticks if you can't still really measure it exactly. So I cannot answer it because it's like a philosophical question, but I can only say that all general relativity is based on the assumption that there is such a thing as an ideal clock, and the whole construction is based on that, and it's kind of questioned this paradigm. So what it means, I really don't know. That's kind of related. I don't know. I mean, in principle, it is possible that you have something that you just cannot measure, right? That there is this elusive quantity that is beyond our reach. I mean, it is possible that it exists but cannot be measured, although, I mean, it doesn't make much sense to discuss it. So, I mean, if you think about physics as a way to kind of describe what we can measure and access, then this kind of goes beyond physics, talking about that. Good question. To me, like things in extreme situations involving extreme acceleration, extreme gravitational fields, causality also should break down at some point. If you try to kind of incorporate gravity and quantum theory, this already leads to serious problems. For instance, you can have photons at two places at the same time, right? We know that experimentally. But what if you had a black hole at two places at the same time? If you could take a black hole and somehow split it on some sort of beam splitter, then you have a black hole here or here at the same time, which means that the time is delayed here, and at the same time the time is delayed here. So that affects all reality, that you kind of have the time dilation that is at the same time slowed down here, and at the same time slowed down here. So that affects causality, and cause of events can be reversed or not even have right, well-defined causal structure. I mean, these things you encounter when you try to combine gravity and quantum theory. The problem is that nobody knows the quantum theory of gravity, so you can only speculate. But any speculation of any sort always leads to interesting and intriguing consequences like this. So I think at this stage, nobody knows the answer to these questions. We know that's very interesting. We are very interested in finding out, but really nobody has an idea how to answer these questions in a way that could be measured, verified experimentally.
So the last question?
So if photons can exist at like two different places at once, then what is your take on like teleportation, like in case of humans?
Well, teleportation is like quantum teleportation is a known protocol that involves teleporting information about the quantum system from one quantum system to the other one. So this protocol exists. It's not exactly what we know from science fiction movies, but what it does is basically you have to prepare two bunch of matter here and here and encode some information somehow in this piece of matter, and this whole procedure takes that information and transmits it to a distant location without destroying the matter itself, but like removing all the information from this this part of matter. So it's information is gone from here to here. That's quantum teleportation. So in case of humans, that would involve us being completely destroyed, like turned into dust, and recreated somewhere else via this whole protocol of quantum teleportation. This whole protocol involves certain time. There has to be certain time that lapses from the destruction to the recreation of the quantum information at a distant location. And well, I don't know what happens in the meantime. Probably nothing really pleasant. But we are still very far from such a practical application of this protocol. So far, we have been able to teleport state of single particles, but not more than that.
Great. Okay, so, oh, yeah, sorry, so did you get a chance to ask David Lynch what he thinks about quantum mechanics?
No, I asked him what he thinks about Poland, and he loved it. I didn't talk to him about quantum physics. But he has a lot of opinions about it. He's like a very spiritual person, so I know he's involved in kind of a lot of philosophical and Eastern kind of philosophical ideas, so probably he has some opinion.